Chapter 3, Laws of Motion. Let us talk about the first subheading, Equilibrium of Concurrent Forces. If three forces P, Q and R are acting on an object such that forces are concurrent and the object is in equilibrium, then P by sine alpha is equal to Q by sine beta is equal to R by sine gamma. Please refer to the image on the screen. Now let us move on to the next heading, Applications of Newton's laws of motion. The strings connected to pulley are considered as ideal. Their length is fixed, so the ends of string follow a fixed relation between displacement velocity and acceleration. These relations are called constraint relation. Now these applications of Newton's laws of motion are explained by three different cases, case 1, 2 and 3. Let us talk about case 1 first. Please refer to the image on the screen for case 1. In case 1, when the middle end is fixed, x1 is equal to x2, v1 is equal to v2 and a1 is equal to a2. For the second case, case number 2, please refer to the image on the screen. When the side end is fixed, x2 is equal to 2x1, v2 is equal to 2v1 and a2 is equal to 2a1. For case 3, when all the three ends are free to move, please refer to the image on the screen for case 3. x1 is equal to x2 plus x3 divided by 2. v1 is equal to v2 plus v3 divided by 2 and a1 is equal to a2 plus a3 divided by 2. Now here is a small note here. In all the above relations, downward direction is taken as positive. If any of the direction is upward in any case, then negative sign must be incorporated in the corresponding equation. Okay, now let us talk about the first formula or the first solution to a problem. A machine gun fires n bullets per second with speed u and mass of each bullet is m. Refer to the image on the screen. Now here, the force required to keep the gun stationary is F velocity is equal to nm v velocity. Point number 2. Please refer to the image on the screen for point number 2. Bullets moving with a speed v hit a wall normally. Now here in the first case, if the bullets come to rest in wall, then force on wall is equal to nmv. Here, n is number of bullets hitting the wall in 1 second. Now in a second way, if the bullets rebound elastically, refer to the same image, force on wall is equal to 2 nmv. Let us move on to the third formula. Liquid jet of area A moving with speed v hits a wall. Refer to the image on the screen. Now in the first case, force required by a pump to move the liquid with this speed is F is equal to V dm by dt is equal to V into rho AV equal to rho AV square. Point number 2. As jet hits a vertical wall and does not rebound, the force extended by it on the wall is F wall is equal to rho AV square. Point number 3. When water rebounds elastically, F wall is equal to 2 rho AV square. Point number 4. Refer to the image on the screen for point number 4. For oblique impact as shown, F wall is equal to 2 rho AV square cos theta. Now let us move on to the fourth formula. The blocks shown are being pushed by a force F. F1, F2 are contact forces between M1 and M2 and M2 and M3 respectively. So, A is equal to F divided by M1 plus M2 plus M3. F1 minus F2 equal to M2A, where F1 is equal to whole M3 plus M2A, or F2 is equal to M3 divided by M1 plus M2 plus M3 F, and F1 is equal to whole M2 plus M3 divided by M1 plus M2 plus M3 F. Now let us move on to the fifth formula. Refer to the image on the screen for the fifth formula. The strings are massless. Let T1 and T2 be the tensions in the two strings and small a be the acceleration. So here A is equal to F divided by M1 plus M2 plus M3. T1 is equal to whole M2 plus M3F divided by M1 plus M2 plus M3, and T2 is equal to M3F divided by M1 plus M2 plus M3. Formula number 6. Tension in the block at a distance x from left end is given as A. Refer to the image on the screen. Tx is equal to mx by L into F by M is equal to Fx by L. B. Tx is equal to F whole L minus x divided by L. And C. Tx is equal to F1x divided by L plus F2 whole L minus x divided by L. We move on to the seventh formula. For the seventh one, refer to the image on your screen. 7a. When system is stationary, T minus mg is equal to 0. 7b. When system moves up with acceleration a, then T is equal to m whole g plus a. And 7c. When system moves down with acceleration a, then T is equal to m whole g minus a. Formula number 8. Refer to the image on your screen. Now the tension in the rope at a distance x from free end is given below for different cases. in case A, in stationary system, Tx is equal to msgx divided by L. For case B, if the rope is accelerating upwards, then Tx is equal to msx divided by L whole g plus A. And for case C, if the rope is accelerating downwards, then Tx is equal to msx divided by L whole g minus A, where g is greater than A. We are now going to discuss some important problems. The first problem is the pulley mass system. This is divided into 4 cases. So let us talk about case 1 first, that is the stationary pulley. You can refer to the image on the screen for case 1. A is equal to m2 minus m1 divided by m2 plus m1 into g. T is equal to 2 whole m1 m2 divided by m1 plus m2 into g. Case number 2. When pulley is moving upward with acceleration a0. T is equal to 2 whole m1 m2 divided by m1 plus m2 into whole g plus a0. The acceleration of each block with respect to pulley is AR is equal to m2 minus m1 divided by m2 plus m1 whole into whole g plus a0. The absolute accelerations of the two blocks are A1 and A2. A1 is equal to minus whole A0 plus AR. A2 is equal to AR minus A0. Now here the value of A0 is equal to whole A1 plus A2 divided by 2. Case number 3. Please refer to the image on the screen to understand case number 3. T is equal to m1 m2 g divided by m1 plus m2 into whole sine alpha plus sine beta. A is equal to whole m2 sine beta minus m1 sine alpha divided by m2 plus m1 whole g. Case number 4. 2 into acceleration of A is equal to acceleration of B. Mass of A into G minus 2T is equal to mass of A into acceleration of A. T is equal to mass of B into acceleration of B. Let us now move on to the next important problem after pulley mass system. Now we will talk about two block system. Now this is explained in two cases, case 1 and case 2. Let us talk about case 1 first. For case 1, refer to the image on the screen. Let small m does not slide down relative to wedge capital M. The force required is given by F is equal to whole capital M plus small m into g tan theta. A is equal to g tan theta in horizontal direction with respect to ground. Contact force R between small m and capital M is R is equal to mg divided by cos theta. Now let us move on to case 2 for two block system. Now in case 2, minimum value of f so that small m falls freely is given by f is equal to capital M g cot theta. Wedge capital M moves with acceleration is equal to g cot theta. The block falls vertically with acceleration g. Contact force between capital M and small m is 0. Angle of repose. Consider a situation in which a block is placed on an inclined plane with coefficient of friction mu. The maximum value of angle of inclined plane for which the block can remain at rest is defined as angle of repose. Two blocks placed one above the other on smooth ground. Now in this case, case 1, please refer to the image on screen for case 1. If a force F is applied on lower block, then A, F lesser than equal to mu whole m1 plus m2 into g. Both blocks move together with same acceleration. A is equal to F divided by m1 plus m2, where A max is equal to mu g. B, F greater than mu whole m1 plus m2 into g. m2 moves with constant acceleration a2 is equal to mu g. m1 moves with acceleration a1 is equal to F minus mu m2g divided by m1. m2 slips backward on m1. Case 2. If a force F is applied on upper block, please see the image on screen. A, F lesser than equal to mu whole m1 plus m2 into m2 divided by m1 into g. Both blocks move together with acceleration. A is equal to F divided by m1 plus m2 with A max is equal to mu m2 divided by m1 into g. B, if F is greater than mu whole m1 plus m2 into m2g divided by m1. Then m1 moves with constant acceleration a1 is equal to mu m2 divided by m1 into g. m2 moves with acceleration a2 which is equal to F minus mu m2g divided by m2. And m2 slips forward on m1. Now let us move on to the next subheading. Minimum force required to move a body on a rough horizontal surface. Please refer to the image on screen. F cos theta greater than mu r, where the value of r is equal to mg minus f sin theta. F is greater than equal to mu mg divided by cos theta plus mu sin theta. and F minimum is equal to mu mg divided by root over 1 plus mu square, where theta is equal to tan inverse mu. Dynamics of circular motion. The first point here is neglecting gravity. T is equal to centripetal force is equal to mv square divided by r equal to m omega square r. The second one is considering gravity with the help of a conical pendulum. You can see the image on your screen. T sin theta is equal to m omega square r, T cos theta is equal to mg, and T is equal to mg divided by cos theta. A. For theta to be 90 degree, that is, if the string has to be horizontal, T is equal to infinity. Therefore, it is not possible. B. T sin theta is equal to m omega square r, which is equal to m omega square L sin theta. Thus, T is equal to m omega square L. C. Time period is equal to 2 pi root over h divided by g, where the value of h is equal to L cos theta. Let us now talk about vehicle negotiating a curve on a banked road. The maximum velocity with which a vehicle can safely negotiate a curve of radius r on a rough inclined road is Vmax is equal to root over Rg whole mu plus tan theta divided by 1 minus mu tan theta. Now in special cases, please refer to the image on screen. For a smooth inclined surface, mu is equal to 0. Thus, Vmax is equal to root over Rg tan theta. And for a horizontal rough surface, theta is equal to 0, where Vmax is equal to mu root over Rg.